Welcome to the third and final video for this week's lecture content. So far, we've talked about the tools that we use to capture motion, and we've learned about digitizing and sampling rates. Now, in this last video, we'll learn about calibration and different scaling errors. Keep in mind here that we're still talking about motion capture and the different tools that we use for motion capture. First off, calibration means to correlate to a standard. So, to apply a calibration, you need to have some sort of calibration standard. If we take the motion capture system from the lab, for example, we need to correlate each of the cameras with a calibration standard, which is what the picture on the right here is showing. So essentially, the goal of the calibration for the motion capture system is to have all the cameras measuring the same position. So we calibrate the cameras by correlating what each of the cameras thinks the position should be with this known standard position, this known distance between the markers on either end of the sticks here. That's the calibration standard that we use to calibrate the camera system. We can apply that same calibration technique with pictures. You just need to have an object with known dimensions in the same plane of motion as your object of interest. And that object with known dimensions would act as your calibration standard. So in this case, Tim Allen is standing in the same plane of motion as this cardboard box that has a known dimension of 1 foot. So based on that calibration, we'd be able to figure out Tim Allen's height. So I don't recommend you pile a bunch of boxes to measure someone's height. I'm just proving a point here about calibration. But yeah, the idea is the same. You can stack 6 boxes before they reach Tim Allen's head. So you know that he's no taller than 6 feet. Now, you could get an exact measure of his height by seeing how much of that top box is required to meet the exact height of his head. But hopefully you get the idea here where you can use this known object of reference to calibrate a different object that you have no idea about. So the last thing that I want to talk about in this week's content is scaling and the different errors that are associated with scaling. So you can think of scaling as the sizing of the image that you're producing with your motion capture device. You can imagine that the angle, the distance, the position of the recording device, for example, your camera, will change the outcome of the image or of the data that you're trying to capture. And there are 3 common types of scaling errors that I want to discuss. There's error from noise, there's out of plane error, and there's perspective error. So let's break each of those down here. The first one is noise. Now, this isn't noise like the sound that you hear, it's a different kind of noise. In this case, noise refers to irrelevant or meaningless data. And that noise can be caused by different things like errors locating the same point in sequential images. If you locate, for example, the knee to be in a slightly different position in 2 different images, then you'll have some error that's caused by noise in your definition of the location of the knee. If you're recording with the motion capture system and you're placing those little markers on someone's body, it's also possible that their skin moves while you're recording, and this would change the location of that little marker and therefore the position. This is known as skin motion artifact. And the last scaling error that's caused by noise is the resolution of the image. So the resolution of the image is like the image quality. It's the amount of pixels or the amount of little tiny squares that are captured by the camera. And the more pixels there are, the higher the resolution, which means the clearer or better quality the picture is. And this down here is just an example comparing the resolution of different images taken of the letter R. So on the far left here, the resolution is just 1 by 1. So just 1 pixel or 1 big square. And clearly you can't make out anything about the image here because the resolution is just too low. Now in the middle, you have a resolution of 10 by 10. So 10 squares vertical by 10 squares horizontal for a total of 100 squares in this image. With this resolution, you can sort of see that the image has a letter R, but the resolution is still not quite high enough that the image is nice and clear. On the far right here, the resolution is much higher. We have 100 pixels vertically by 100 pixels, horizontally. So now the image is crystal clear and it would be easy to pinpoint a specific part of the image for digitizing. So that's the resolution of the image. Okay, so the next type of scaling error is out of plane error. And we know that we have to be perpendicular to the motion that we're observing, but we also need to be at an appropriate distance. If we're too far, we'll miss certain specific parts of the motion, just like if we're too close, then we won't see the full picture or the full motion itself. So this idea of having the right distance is known as an out of plane error. And the last scaling error is perspective error. And this goes back to being perpendicular to the plane of action or the motion. So see how here there are 3 different views of the same 2 lines. Think of this as your arm, where the elbow is the intersection here of those 2 lines. So if you're perfectly perpendicular to the motion, then you have a nice side view and you can tell exactly how your upper arm and forearm are positioned. If you're not totally perpendicular, if you're slightly on an angle or a partial side view, then the position of the arm and the forearm as you see it through the lens of a camera, it changes. It looks like there's a different elbow angle here than there would be in this case. And again, the front view is even harder to make out. You can barely tell that there's an upper arm and a forearm in this case, and you definitely wouldn't be able to determine the elbow angle. So here's an example of what I mean. We have these 2 different chapsticks that are in the exact same plane. The picture is taken directly perpendicular to these 2 objects and they look the exact same. Now, if one chapstick is closer to the camera than the other, your perspective changes. It now looks like the one on the left is bigger than the one on the right, even though we know that in reality they're the same size. The camera, in this case, isn't perfectly perpendicular to both objects, so this causes a scaling error between the 2 objects. Here's another example where the position of the camera changes, and it looks like the size of the chapstick changes, when in reality, it's the same chapstick in each of these 4 pictures, it's just taken from a different angle. Okay, so that brings us to the end of the week 4 content on motion capture and digitizing. In this video, we learned about calibration and scaling, focusing specifically on scaling errors. To supplement this week's content, I've added a demo of the motion capture system that we have in our lab, where I do my research on the 3rd floor of the Kin building. And I've also added some other videos that you might find interesting, like how they make different CGI movies and video games based on motion capture equipment that's exactly like the one we use in biomechanics. Before I end this week's video, I just wanted to take a step back and give you a sense of where we're at in the course. So far, we've learned about anatomy, qualitative biomechanics, and motion capture. Those are all very important and fundamental concepts to know in biomechanics, but we haven't really delved into the meat of the course just yet. On the right here, you'll see that we have 5 topics left to learn. We have linear kinematics, angular kinematics, forces, linear kinetics, and work power and energy. So for the rest of the topics, we'll be applying mathematical and physics concepts to solve these problems. So if you haven't already, I strongly encourage you to complete the review worksheet that's found in the introduction folder on OnQ to make sure that you're up to speed on the basics like trigonometry and BEDMAS before we jump into the next topic. Now, I'm really not trying to scare you by saying this. You don't need to be a mathematician to do well here. You just need to know how to apply certain concepts that you've already learned in high school. And for every topic, you'll have the opportunity to make sure that you grasp the concept by completing the check your understanding activities. And remember that these activities aren't worth any grades. They're really just there to help you. Okay, on that note, see you next week.